So hello, hi guys. This is Marcus here. We are at the office hours for Oracle Machine Learning. And today we have a very cool session. So Jie is going to show the machine learning concepts using cross-validations with OML in database and with embedded Python execution. And my name is Marcos Arancibia. We're supporting Jie with Sherry and Mark. So at any point of the presentation, if you guys have questions, please don't hesitate to ask them in the Q&A, okay? So the agenda for today is simple. We wanted to make sure that we talk to you about one thing before we start with the cross-validation, which is the new Italian language support. So the Oracle Machine Learning Services has rolled out last week support for Italian language in the cognitive text. So I'll do a quick demo to you guys, and then I'm gonna pass that on to Jie. Okay, so real quick, here I am in my Postman, and in Postman, after I get my token, you guys can see that the collection number 6 has been expanded, right, from the original text and keywords in English, right, that we were normally using, and then we did some text keywords in Spanish, and we had that keywords in French. So all of these guys are still there. Then what we have done now is we have added the Italian language. So now we have text keywords in Italian, okay? So for that, you need just to say the set language to Italian, and then you put your text in Italian and just send it, and then we're gonna get back the results. So in this case, dati, data, database, algorithmi. Then you get summary here, right, with the same kind of capability. So now we get the sentences, right, for summaries. So it's going to look into your text and find what are the sentences that actually make a good summary of the text, right? And then text topics, same thing again. Make sure to say language Italian, and then you're going to get your topics, right? Oracle Corporation, database, big data, base di conoscenza, apprendimento automatico, and then text similarity, same thing here. So I'm trying to look at the similarity of the algorithm, the apprendimento automatico in a database with the entire text. And then I get that similarity. And then finally the features, right? So the 1024 features that we get back from the Wikipedia model, okay? So very simple. I just wanted to show that to you guys and mention that I'm adding that. So the collection has been pushed to GitHub. I imagine it's going to be there in the next day or two. So you're going to find that in our GitHub repository. Okay. All right. So Jie, with that, I would like you to take it away. And thank you for presenting that to us.
Sure. Thank you, Marcos. Hi, everyone. Thank you for joining. My name is Jie Liu. I'm the data scientist working with Oracle Machine Learning. I don't know Italian, but I know a little bit about the data science. So today we'll share with you some experience, some very cool features in OML for Pi when you do cross-validation. So the outline of this talk is we first go through some several theory. I know many of you may be very familiar with the cross-validation, but I think it's fine to look back at the concept. And personally, I find when I review these concepts, I think it's just inspires a lot of consideration and rethinking about the process. And then I will show you how we do cross-validation. You have an algorithm in database, and then also you can use the embedded Python execution, also run the open source, both open source and in database solution. So the motivation for cross-validation or even model validation is that the entire data science practice and needs a scientific way to validate the performance before you put data science solution or machine learning projects online, the first thing you want to do is you want to validate the model is correct. The whole algorithm, the whole pipeline is working. You can't just push the model without second thought into production. You will never know what will happen if you don't validate the model first. But how to evaluate the performance of the model? And usually when we develop the model, with a lot of things we can change. Sometimes you may select the ML algorithm. Sometimes you can adopt a new or cool feature engineering. Also, you can tune the parameters. There are many things you can change. But we want to make sure that everything you changed, you may have a good way to know whether this change bring you improvement or not. Think about this three scenario. A data scientist report to you, he spent the entire week, maybe try a new algorithm library. You see the EUC increase from 0.71 to 75. Or maybe he said, I created 10 features and I increased the recall, from 0.73 to 0.82. Or like he choose like a random search method to find a better set of parameters. And you see always there's increase of this performance. But the thing you want to ask is that, are those improvements really significant or reliable? And maybe this time he sees the improvements. Maybe next time when the new data come in, this improvement may not be that significant. So we need to have some way to validate the methodology. The first principle, of course, is that you build the model on the current existing data set, but you can't just using the data set you use for training to validate the model. So you will get into trouble because think about nowadays how powerful the ML algorithm is, like the deep learning neural network. People have done research like even you put random labels on each data set, each data rows, deep learning model can still fit very well and give you perfect results, very high accuracy. It only guarantees that you do well on the training set, but you can't guarantee that it will work for a new data set. So this is the first principle. You can't train the model and validate the model on the same data set. So the correct way to do is you always split the data into training and test sets, following some ratio. Train the model on one data set and then test the test model on the test data sets. And also one thing I want to highlight is that we probably need to guarantee that the distribution of these two data sets, especially for the label distribution, should be roughly the same. This will be very important when you work with very highly imbalanced data set. Think about if you only have 1% of positive labels, when you split the data sets, it's very possible that maybe all the positive labels get into only training data set or like test data set. So you have to use something like a stratified sampling to even distribute the positive labels. So although we have this approach, but there's still some drawback. The main drawback is that you only have one split, right? You only have one set of training data set and one set of test data set. So you only have just one result, right? But think about all the pipeline you have designed. Usually the machine learning model and also the some model in itself is in nature is random, and also the data set you're using, there's always some randomness in it. So we are seeing when we think about the model performance, it's actually a random variable. If you want to know the random variable, you need to have multiple measurements instead of just one measurement. Just one measurement won't give you too much information. And in this case, it's maybe highly dependent on the this particular split. Maybe in a different split, the model performance may behave differently. And also you want to have a sense of variation, how the performance varied, through different split. So that's why people propose maybe we can think about a way to have multiple measurements. One way is you just leave one sample as a test point, and then the training on the rest of the data points. So in this way, you have a lot of measurements coming in. And the benefits also is the training data you're using roughly the same, right? It's only just every time it's just one little bit of a change. To give you a low bias in the estimation of a prediction error. The drawback, of course, is that this is prohibitively costly, right? You can't, usually the number of rows in the usual data science projects is huge. But basically people don't do that because this is too costly. In reality, people usually use k-fold cross-validation. So you can think about this is the mitigation of the previous problem. Instead of using just one sample as a data test set, we just split the data set into k parts. So each fold, we use one fold as a test data, and then use the rest as the training data. The benefit, of course, you can reduce the computational cost. But the drawback is, it's slightly overestimated the prediction error, right? Because every time previously you are using most of the training data. Right now you are losing one set of training data. So it's in this case you have a fewer data for training. You have a potentially overestimate the prediction error, but it's okay. It's a price we pay. It's something we can accept. Usually empirically k equal to 10 and also with some stratified sampling on target will be highly recommended. This is not, there are no proof in it, but people show that in some papers. The one thing I want to highlight is the cross validation is not something you want to apply for every project. For some data, it's sensitive to time, like data with timestamps. You probably can't do that because otherwise, think about this as the time axis. Sometimes you are using future data to predict the past data. This is not acceptable. So in that case, you probably need to use other methodology like you maybe use some sliding window and move forward to strictly make sure that your training data is older data, right? So, but today we will focus on the k-fold cross-validation. So in OML for Pi, we provide very convenient APIs. Also, I want to highlight is that even you have even k-fold cross-validation reduce time cost, computational cost, you need to repeat everything k times. For the 10, k equal to 10, this is 10 times of your time cost, your original time cost. This is still a lot. In reality, we want to, every time if we want to change something, we want to make sure we know the results faster. So the idea is, we can parallelize the k-fold cross-validation using embedded Python execution. It will help you to improve the performance. So next, I will show you some quick demo. So this is the data set we want to use. it contains some demographic information of the customer. And the goal is we want to predict whether they want to buy insurance or not. So yeah, this is just transform this yes or no into 0, 1 for convenience. So you create this subset of this table. And yeah, so here this is the API I want to use. This is a keyfold function. It's just kind of a little bit similar to the sklearn API, but it adds some several capability together. So here you want to tell him, kfold, how many fold you want to use, and also this is the strata columns. So this is usually the target column. So that's help you to evenly distribute the class target distribution into different space. So we got this output. So this output is actually a list, right? And because we have a 10-fold, we have this list have length 10. Each of them is a tuple. The tuple is actually a pair. This is the first, in this pair, the first one is the training set. Second one is the test set. So just after call it once, you automatically have everything done for you. In case you want to look back, right? If you want to, because when this session ended, this OML data frame will not be available. But you always can create views. You do not need to materialize the actual data. You can just create views for each split. And in case later you want to revisit the data set, you have to split it. Yeah, this is one of the view. Yeah, this function calculates the AUC. It uses the query, and you can achieve that without actually materialize the prediction test set. We are using this function to do all the jobs for us. First you want to maybe just split everything into 3 stages. The first is pull the data. The second is the training. The third stage is scoring. Right now we want to look at OML algorithms. So we do not need to pull the data, right? We don't need to pull. But anyway, I have also added several code to record the time. Yeah, so this is time, record the time, and also do the scoring and calculating the AUCs. So one thing I want to highlight is in Python. One convenient thing is the function is a first class statement. You can pass this function as argument into this function. So in this function, you can add any code you want to train the model, and pass it into this main function and let it run. So here I calculate after I calculate the AUCs, I will save it into the data store. So we can collect them later. Yeah, so this is a single run test. So we don't need to pull the data. It's just to take the time, the training and the scoring, and this is the AUC we get. Also, I added some code to plot the results. The one thing I want to show is I want to make a comparison of whether it will be beneficial to parallelize or not parallel. So this is the parallel or run. As I mentioned, we can use embedded Python execution. So here the function we are using is index supply. So index supply allow you to initiate 10 jobs altogether. What you need to do is just to supply the function you want to run together with all the this argument you want to use. So this here you just tell him time equals 10. Under the hood, it will look, this is the index, right? If you have a 10, it will every time you will have you imagine you have 10 copies of this function running at the same time. Each of them have a unique ID. So the ID will spanning from 1 to 10. And here we are using this one to to find the actual OML data frame. So it's super easy to parallelize everything. And on the right side, I just want to make a comparison or run this for 10 times in serial. Now this code plots the results. So this is the this is the results. So there are the three type of jobs. The pool, we don't need to pool, so no pool. And when we have a train, the scoring takes very little time, of course. So the first one is a parallel run. So this experiment is done under medium. In the medium, you will usually have like 4 or 3 jobs running all together. So running parallel, so the whole thing just finished here, like around 30 seconds. So here, this is a serial run. You can see it takes almost like 2 point, maybe you have a 2.5 times. So that's in reality. You can think about how much time we can save when we test the running in parallel. So next, I will just show you a quick user scenario. Like suppose the data scientists want to compare 2 algorithms. One is decision tree and the other is the GLM. Of course, we run it in parallel, and we can check the result we obtained. So this is because we have a 10-fold, we have 10 AUCs obtained, and this is for decision tree. You can see this is the span, this variation, right? So from this to this is usually so roughly about 0.02 variations. Yeah, that goes back to our early examples. The data scientists go back to you, hey, tell you like, hey, I increased the AUC from 0.79 to 0.82. Well, probably that's just like lying in the variation, right? It's usually if you just do a cross validation, you will vary it that much, right? But if he told you he increased to 0.9, that's another story. But if there's any changes that even included this variation, this scope, then you may have some doubt on his results. Maybe just he's get lucky. Next thing, we want to repeat for that for GLM to see if it have a better results. No, because particularly in this data set, probably in data sets may have a lot of categorical variables. Maybe decision tree may be better. But the thing is, right now we have both understanding of this variation and also the mean. So you can clearly see, this decision tree did a better job, do have a good job. It's not like they're lining together, but they have just well separated, and we can think about this improvement kind of reliable. The next thing I want to show you is we can also do that for if you have an open source algorithm, you can also do that, do the same thing. To make things more significant, I just replicated data into 10 times. So we will not focus on the AUCs, we'll probably just focus on the performance. So here you can, for example, you can just create training random forest, training JVM in the open source libraries. And the same thing you can apply. We want to make a comparison here. So that's the results. Again, it's right now, you can see the dark green part. This is the pool, right? If you use the open source algorithm, the a higher price you pay is you have to pull the data from the table, from the DB. So that's the time you spend on in the pool. But anyway, if you are using the index supply, it still give you a lot of saving in the time. Yeah. One thing I want to highlight is when you're using, if you're using the sklearn algorithms, right now some algorithms have this option, number of jobs. You probably need to keep this number of jobs low, because otherwise, you think about if you don't, you set this very high, one algorithm, one particular copy of this job may grab too many CPUs. So you may not enjoy this benefit of parallel. You probably need to keep this number of jobs low enough to give you a benefit of running that in parallel. Otherwise, think about this just one job will grab a lot of resources, and you won't see the benefit of doing it in parallel. So this is kind of like a trade-off. Yeah, this is just another plot for the you see it here. Yeah, that's my presentation demo. If you have any questions, please leave it in the chat. Hi, Marcus, do we have any questions?
We had quite a few. I think we answered all of them. There was one interesting one asking about the how many CPUs are you using?
Yeah,
because,
this is
and I mentioned already. I answered that it was 16 that your session has, but I don't think you needed all of those, right? I mean,
yeah, in case if you are running the parallel, yeah, I think it's because this is not so you have a two VM. One VM is supporting this notebook right now you're using. There's another one responsible for the index supply. It holds all the Python engines. Yeah, if you're using index supply, you have two VMs working for you. Yeah.
Right. So what I mentioned was that as long as you have auto scale on, right, in your autonomous database, that you should be able to get some parallelism for sure running.
Yeah.
So we now have one that says, can we achieve k-fold with OML for SQL? If so, do we have any sample notebooks for the same?
Yeah, for SQL, I don't. But for SQL, that's another. You need to adopt another approach, which is using the DBMS scheduler. And also, you can initiate. DBMS scheduler is supposed to give you benefits of kick off several jobs like this. Another way is you can create your own Python script. That's what I tried. You can just leverage the multi-thread capability of Python.
Mm-hmm.
You kick off 10 threads. Each thread you start a DB connection, and using CX Oracle running script.
Excellent.
Yeah, both will do.
Yeah. Another one is what about data preparation? Should we apply it after n-fold splitting?
Yeah, that's
for example, normalization, quantile binning, and things like that.
Yeah, exactly. That's the one thing I didn't cover because it's relatively complicated. The thing you want to keep in mind is that the data preparation, all the operations you did should be keep consistent with the cross validation. So every time you do the preparation, you need to keep in mind you have to limit the scope within the training data. You can't calculate some feature using all the data and then you do the cross validation. Yeah, it's wrong because you're leveraging more information. You have to only use your current training data to calculate all the feature engineering stuff and then test it on test set.
Mm-hmm.
Yeah.
Perfect. Yeah, that's great. The other question here, do we get an acceptable set of performances when we run cross-validation on artificial neural network and autonomous database?
Yeah, I think that's that thing. One thing. Yeah, I can add some example showing the neural network. I think as long as you have enough number of CPUs, you can still achieve these results. The thing is, as long as each neural network job have a reasonable allocation of those CPUs, you will see these similar results, definitely. The thing you want to avoid is that you have a very huge data set, and you supply it all together. That will not do, because each job will grab a lot of resources, and each of them will start to competing for each other of the IOs, the CPUs. That will not do. But as long as you have a reasonable data size, and number of CPUs allocated, you should be able to see this benefit. Yeah.
Okay, awesome. And I think the last question I'm seeing here is whether OML has deep learning features or models. Well, we're definitely thinking about those things. Those are requests that we get from many customers. So I would argue those would be future capabilities, right? That we would add potentially to the lineup. But for now, the focus of OML is really the in-database algorithms, right? Those are the ones that can handle large workloads and can scale very well, and then allowing you to do some definitely Python, and we have R as well coming up later in the year to work with the embedded execution of those and some of the packages there, right? If that doesn't stop us from eventually having some of the more deep learning capabilities embedded into the components, right? But that's not the focus today. So I think that's it. Just wanted to say thank you very much. It was an excellent presentation. I think people learned a lot, and there were very, very much a lot of great questions. So we're going to make sure, Jie, to get your notebook and post it in the OML Ask Tom sessions, as well as put that into the GitHub like we did, I think, the last time. All right.
Yeah, sure.
So thank you very much. I really appreciate you guys, and see you guys next week, where Sherry's gonna present XGBoost using embedded Python as well for you. All right. Thanks a lot. Thank you very much.